this exploration problem, this is the same code we have in example 5. So in example 5, we found that dy dx equals minus 24x squared minus 16y divided by 16x plus 3y squared. And the way we got to this is we took the derivative of both sides of this equation, assuming that y was a function of x, took the derivative with respect to x and isolated the y prime, which was dy dx. So this exploration says, to redo this example, think of x as a function of y and take the derivative with respect to y. So let's do that. I should say the derivative of 0, which is still 0. So we're going to go through, we'll have the same rules as before. So we're going to use the sum property here. We're going to use the constant multiple rule on the first two terms. Now here I'm taking the derivative of y cubed with respect to y. These are the same letters. So I just use the power rule, 3y squared. There is no y prime here. Well, I guess you could think of a y prime, but since I'm taking the derivative with respect to y, it would just be dy dy, which is 1. So we're treating y now as the independent variable. So let's recopy this onto the next slide. So I'm just recopying this line here. Now, here I'm taking the derivative of x cubed with respect to y. These are different. So I have to use the chain rule because I'm thinking of x as a function of y. So the derivative of x cubed would be 3 times something squared times the derivative of that thing, x prime dx dy. Plus 16, I have to use the product rule. The derivative of the first factor with respect to y times the second plus the first times the derivative of the second with respect to y plus 3y squared is 0. So I got a 24x squared x prime plus 16 times the derivative of x with respect to y is x prime times y plus x times the derivative of y with respect to y, and that's just 1. Plus 3y squared is 0. So I've got a 24x squared x prime plus a 16x prime y plus a 16x plus a 3y squared is 0. And now what I want to do is gather all the x prime stuff on one side, factor out the x prime, divide by the coefficient of x prime. So I see the x primes here. I'm going to have x prime times 24x squared plus 16y equals minus 16x minus 3y squared. And so for the grand finale, I'm just going to divide both sides by the coefficient here, 24x squared plus 16y. So I get x prime equals minus 16x minus 3y squared divided by 24x squared plus 16y. And that's what I'm getting for dx dy. Now for dy dx, I got minus 24x squared minus 16y divided by 16x plus 3y squared. Now let's do a little bit of arithmetic here. I'm going to factor a negative 1 out of the numerator and put the negative out front of the fraction. So remember, negatives float when it comes to fractions because you're multiplying by negative 1. So you can either multiply the numerator by negative 1 or the denominator by negative 1. That's the same as multiplying the fraction by negative 1. Okay? It's because negative 1 is negative 1 over 1 or 1 over negative 1. So that's a little flashback there. So I'm going to factor the negative out front. I'd have a 16x plus 3y squared in the numerator over a 24x squared plus 16y in the denominator. And by golly, if I do the same thing down here, I think you can see the relationship between dy dx and dx dy. They're just reciprocals of each other. Oops, that's the cat. They're getting excited about that. So in this particular case, it certainly appears as if dx dy is just 1 over dy dx, which makes sense on the level of fractions. Remember that dx dy is coming from an infinitesimal limit of delta x over delta y. This is coming from an infinitesimal limit of delta y over delta x. But we're actually looking at two different scenarios, x as a function of y versus y as a function of x. And so at the level of derivatives, the slopes are reciprocals of each other. And this is going to pay dividends for us because later in the semester we're going to come back and talk about the concept of inverse functions. Inverse functions is when we reverse the roles of the inputs and the outputs. We reverse the roles of x and y, and we're going to use this is a theorem that actually generalizes that we'll use later on when we're trying to calculate derivatives of inverses. So it's worth the time to go through it, at least on the video. So that'll do it for implicit differentiation.